Welcome to the course of analysis of several variables. So today we are going to discuss the module 1, which is some topological properties of the Euclidean space Rn. In this module, we are going to study about the fundamental recalls. So we will recall about the basic ideas, which is useful for study the topological properties. Then we have introduction of Rn, then linear subspace of Rn, then basis and dimension of Rn, Euclidean inner product and norm in Rn, and then continuity of functions defined on open subset of Rn. So this six concept is consist of the model 1. So let's start with fundamental recalls about some topics. So we have the first topic is vector space. So a set V with binary operation, and we call it as scalar multiplication. Start binary operation plus additive and scalar multiplications is said to be vector space over a field F. So this field is maybe real or complex, but as we are discussing Rn, so we'll take the field F is here in this course as R. It follows following properties. So first is V is closed under vector addition and scalar multiplication. What does it mean by the close? That if you take two vectors U and V from the set V and one scalar from the field F, let's scalar is alpha, then if you take the linear, if you take the apply the operation, the vector addition, what is defined here, that U plus V, so what will be the new outcome? That should also belongs to V, means they have the same properties like U and V. And if you multiply this alpha with U, then alpha U belongs to V. So this is called the closure property of the space V. So let's have example here. Just take B is equal C, the set of integer, okay, and F is real number, set of real number. So now we define the addition and scalar multiplication as like this: A plus B is equal AB over 3, and alpha A is equal, alpha A means usual multiplication. Then this V plus dot is not closed. Why? Because A belongs to V, B belongs to V, then A plus B, which is AB over 3. So it may not be always integer. Okay, may not be always integer. For example, let A is equal to and B is equal 5. Then A plus B is equal 10 over 3, which is not an integer. So therefore it is not closed, though alpha A is closed. Okay, so the scalar multiplication is closed, but addition is not closed. Let's have the next properties. Next property is that U plus B is equal B plus U. So it should be commutative. So for example, here we take this V equal G, the set of integer, and F is real number. Define the addition. Define the addition as A plus B is equal A square. Now under this is operation, the set is closed, but it is not commutative. Why? We'll explain it now. let's say a plus b is equal a square b, so which is always integer. If a b belongs to g. Now they are not commutative because let's take a is equal to and b is equal 3. Then a plus b is equal a square, it is 2 square, 3, then 4, 3 is 12. But b plus a, this is equal 3 square multiplied 2, so this is 18. So in this case, a plus b is not equal b plus, hence this is not commutative. Now we have next case is u plus v plus w is equal u plus v plus w. That means if you interchange the position of the vectors and rearrange it, then they must be equal, and this property is known as the associative properties. Now one of the important part is that zero vector or identity vector. So what is the zero vector? Zero vector means that for any vectors u, there exists another vector in the set V, which is denoted as 0v because we call it zero vector. So you have such entries in the set V such that whenever you add any of other element of V, let's say u, then when you add the 0v, it will gives you the same vector. And if you change the position because of the commutative property, if you change the position, then it will be reverse part also give you the identity vector or zero vector. So this entries is known as the zero vector or identity. Example, we take v is equal r and set of real number, and f is also real number. Then we define a plus b is equal a plus b, which is like addition, usual addition of numbers. We are not define anything special. Okay, so we just define as a number 2 plus 3 equal 5. That way we define the operation. Then 0v in this case is equal 0 the real number, as any number if you add with 0 will give the same number, means a plus 0, with by definitions it will be a plus 0 is equal a. So this is always true. So this will gives you 0 is the number 0 is the 0 element of this vector space. Now let's define the the addition is like this: a plus b is equal a plus b plus 2. In this case, 0v is equal minus 2. How it is? Because we have to get it a plus b or a plus 0v, a plus 0v is equal a. Now a plus 0v by definitions it is here a plus 0v plus 2 is equal a. So this implies 0v is equal minus. Okay, let's move to the now next property, which is the inverse. Okay, so the inverse is that like O0v, there exists always a one vector which you denoted as IV, such that if you take any entries of V and add with IV, then you will get the 0v. If such entries exist, then this IV is known as the inverse vector of B, and this must be true for any arbitrary vector from B. This IV should exist. Then this one property will satisfy. Okay, let's have the examples here, like in the previous example. So in the last example, we take V is equal R, and in this case, we got with usual addition and addition of numbers, we got 0V is equal number 0. So therefore, what will be the inverse of these cases? So let's, you have A belongs to R, then A plus IV is equal 0. So this implies IV is equal minus A. So the negative of any number is the inverse. So inverse for 5, inverse for A equal 5 is minus 5, and inverse for minus 5, if A equal minus 5, then IV is equal 5, 5. But if you take this set, which we saw that minus 2 is the minus 2 is the is the inverse. So minus 2 is the 0. So what you will get here, A plus IV. So you will get, should be minus 2. So this implies IV is equal, so this implies A plus IV plus 2 is equal minus 2. So this will give you IV is equal minus A minus 4. So IV is equal minus A minus 4. Okay, let's have the remaining property. Property 6 is that this addition property with scalar multiplication is distributive. So alpha u plus b will be alpha u plus alpha b. So these are easy to verify. We are not going to verify. Same way, the scalar addition alpha plus beta over the vector u will be alpha u plus beta u. And if alpha beta multiply with you, and then if you exchange it, then the outcome will be same. And the last property, which is multiplicative identity, is 1u is equal u. So this all about if any set with these two binary operations satisfied this 9 property, then we called it a vector space. So you have done in linear algebra and many other courses this many examples. So we are not going to details of the examples. We just need these definitions for this course study. So similar way, we will just recall few other definitions, and next definition is linear combination. So if you have a set of vectors v1, v2, vn, and the n scalar alpha 1, alpha 2, alpha n, then the expression written as like this: alpha 1 multiply v1 plus alpha 2 multiply v2, and so on. So this expression is known as the linear combination of the vectors v1, v2, vn. So if you say w, and if you say the it is a v is from a vector space, then by the closure property, as we discussed in the previous slide, so this linear combinations, which will gives you a new vector which is belongs to the vector space V by the closure properties. Our next definition is linear independence. So if you have a set of vectors like the previous one, that v1, v2, vn, and this set will be linearly independent if the linear combination, as we defined in the last slide, that linear combination is 0. So 0 here, or the number 0, 0 is the 0 vector. If it is 0, provided this all the entries are 0, C1, C2, Cn will be 0. This is 0 number, and this is, you can say, 0 B. So now if such linear combination is possible, then we say that this set is linearly independent. Next is the spanning set. Let S be a set of vectors from a vector space V. If any vector V belongs to V can be expressed as a linear combination of vector of S, then the set S is known as the spanning set of V. For example, let V is equal R, set of real number, and S is equal, the single set is 1. Then if you take that any vector of V can be expressed as the linear combination of S. Let's say 5. So 5 we can write it as 5 multiply 1. So any number if you take 6, 6 can be written as 6 multiply 1. So therefore S is a spanning set of B is equal R. Now this set, if this set is linearly independent, then we have a one specific definition that called the basis. So subset S of a vector space V is called basis of V if S is linearly independent and S is spanning set of V. So therefore S is equal 1 is a basis of V is equal R. This have a number of elements, and that number is known as the dimension of V. So since S is equal 1 is a basis of, as we discussed just above, basis of V is equal R. So therefore dimension of R is equal 1. We can have many other examples. For example, V is equal 1 x square is, sorry, S is equal is x square is a basis of V is equal P2x, that is space of all polynomial of degree less than equal to less than equal to 2. Okay. So therefore the dimension of P2x is equal 3. In general, dimension of Pnx equal n plus 1. Now, another important aspect of this fundamental is that subspace. So we called a subset of a vector space V is a subspace if with the same operation of V, that is the addition and scalar multiplication, W is closed. That is, if W1, W2 belongs to W and alpha belongs to F, then the scalar, then W1 plus W2 should be belongs to W and alpha W1 belongs to W. You may think that it is obvious, but it is not obviously true. For example, if you have this is V and this is W. Now you take W1 here and W2. Now since W1 W2 is a member of V, so W1 plus W2, it is member of V because V is a vector space. But it is not guaranteed that W1 plus W2 belongs to W again. So if it is, then and along with this second property, then we can say W is a subspace. Means W is a vector space, or W has satisfied the closure properties with respect to the addition and scalar multiplication, which is defined on its superset V. So if it is satisfied, then it is known as the subspace of the vector space V. If these two properties are satisfied, then automatically other properties of the vector space is satisfied. So therefore W is known as the subspace of V. So therefore, to show that W is a vector space, it is enough to show these two properties. Okay, so this we finish the fundamental recall of the vectors which is required for this. The second topic for this course is introduction of Rn, and then we'll have linear subspace of Rn, basis dimension, and equally linear product in Rn, and then continuous functions. So before going to the Rn, we discuss about the cross product. So two sets A and B, the cross product is given as AB in a pair where A belongs to A and B belongs to B. So the elements of A and B. So as an examples, let's have here R2, which is given as R cross R. So here A belongs to the real number and B belongs to the real number. So this can be graphically present as like this. So let's R in the x-axis and R also in the y-axis. Then take A as x, value of x, and b as a value of y, then the pair A and B is given as the member of R2. So since we can take any arbitrary A and arbitrary B, so therefore whole plane will represent as R2 cross R2. Now this idea can be extended to R3, R4 and so on Rn, where R3 can be written as R cross R, and R4 is R cross R cross R cross R, 4R. Next we will try to get that how we can write the elements of Rn. So let's X is a member of Rn, then X can be written as x1, x2 and so on up to xn, that is n number of the entries. Or in some cases we also write it in the column vector as x1, x2 and xn in a single column. For example, R3 0 0 0 belongs to R3, 1 2 5 this is belongs to R3, 1 2 4603. So this is, you'll see there 6 entries there, so this is belongs to R6. Now we can write 1111, so this is belongs to R4. Next, we need to know the algebra of Rn, the entries of Rn. So let x is x1, x2 to xn belongs to Rn, and y is equal y1, y2 and yn belongs to Rn. Then the addition x plus y can be given as x1 plus y1, means for addition of the first entries, then addition of the second entries, and continue addition of the nth entries. So each entry you have to add with similar position entries, then we can define the addition on Rn. And the addition also belongs to the set Rn. For example, let's 1 to 4 plus 3 to 1, which are members of R3, and if you add them, it will be 1 plus 3, 2 plus 2, and 4 plus 1, which is 4, 4, 5, and it is also member from R3. If x belongs to Rn and y is Rm, then x plus y is defined if n is equal m. For example, x belongs to R3, y belongs to R4, then x plus y cannot be defined. Next is that how to define the scalar multiplication on Rn. So let's x is equal x1, x2, xn. This is belongs to Rn, and alpha is field, which is from the field which is here is real number. Then alpha x, the scalar multiplication scalar alpha with vector x can be given as alpha x1, alpha x2, and alpha xn. That is, the each component of the entries of x will multiply by alpha. If we write in the column form, then it can be written as alpha x1, second row alpha x2, and then nth row is alpha x. So if xy belongs to Rn, then x plus y belongs to Rn, and alpha x belongs to Rn. So therefore the scale measure as well as the addition are close to Rn. So therefore Rn is a vector space with usual addition and scalar multiplication. The previously the addition defined in the previous slide, and the scalar multiplication, that is known as the usual addition and usual scalar multiplication. Okay, so now the question is, if it is a vector space, then what are the zeros of Rn? The zeros of Rn is given as 0 Rn, which is equal 0 0 0. That means n entries of 0. Okay, and the inverse of this entries is given as, means if for any x belongs to Rn, the inverse will be the negative of that vector. So negative means here minus 1 we have to multiply, and by the scalar multiplication you will have minus x1, minus x2, and minus xn, which is also belongs to Rn. So therefore minus x is the inverse of the vector x belongs to Rn. So x belongs to Rn, there is minus x for that vector which is the inverse of that x. For example, x is equal to 5 minus 6 3 and R4. Then inverse of x is minus x, which is minus 2, minus 5, 6, and minus 3. Now if you see that if I add x plus minus x, then it will become 0, which is the 0 or identity element of R4. We finish the second section, introduction of Rn. Now we'll move to our third section, which is linear subspace of Rn. So first we'll give you definition. So a subset E of Rn is known as linear subspace of Rn if the 0 of Rn belongs to E and x plus alpha y, the linear combinations of two vectors x and y, which is also belongs to E. Okay, so let's have examples here that will show that which is subspace, which is not subspace. So we take W is a subset of Rn with the conditions that that first entry is x1 is equal 0. So W, capital W, contains all the entries from the Rn in which the first component is 0. So we have to show that this is a subspace of Rn. So since x1 is equal 0 and x2, x3, xn all can be any number which is belongs to R, which is belongs to the set W, which is Rn, and specifically if first one is 0, then it will belongs to W. Now if we take so clearly if x2, or you can say generally xi is equal 0 for all I is equal to 3 and up to n, then the entries x is equal 0 0 0, which is belongs to set w. That means 0 odd n is belongs to w. Now if you take y is equal 0, y1, y2, y1 is 0, y2, y3 and yn, which is belongs to w, then x plus alpha y for any scalar alpha, you will get the addition as 0, because 0 plus alpha 0, it will be 0, and then you will have x2, x3, xn, and 0 alpha y2, alpha y3 and alpha yn. So if you add them, so you will get it 0, x2 plus alpha y2, x3 plus alpha y3, and so on. You will get xn plus alpha yn. So therefore the first entry is here 0, and we can say that this addition x plus alpha y is a member of w. So therefore w is a subspace of Rn. Okay, now come to our next example, and in this case the first entry is greater than equal 0, and we have to show that this is not a subspace, or we will verify that it is a subspace or not a subspace. Okay, now since x1 is equal 0, so clearly the first entries can be 0, and other entries since from any real number x2, x3, xn are any real number, so therefore that they can be 0. So therefore 0 0 0, which is the 0 of the vector space Rn, can be a member of W. To show the other properties, we can take it by examples. We take 1, x2, x3 and xn belongs to w, because the first entry is greater than equal 0, so we fix it any number. You can fix it in by any number, and we fix it, the first one is 1, and second entries we are taking, the first one is fixed by 2, and the other entries are y2, y3 and yn, that belongs to w. Now we will try to do the scalar we will try to do the linear combinations of these two vector by taking, let's say, alpha equal -1. So therefore you got the first entries minus second entries, so x plus alpha y, which will be x, which is 1, x2, x3, xn, minus 2, y2, y3 and yn. So then we will have here -1, x2 minus y2 and so on, xn minus yn. So whatever x2 minus y2, x3 minus y3, we don't bother, but the first entries is -1, which is negative, so it does not belongs to w, as that condition of the w is that the first entry should be non-negative. So therefore w is not a subspace of Rn. Now another example is here, that the subset w is equal from Rn, and the condition is that the first entry is x1 is the x2 plus 1. So in this case we have to show that it is not a subspace. So first we will try to see that 0 is of Rn is belongs to this W or not. So for that we take, let x2 is equal 0, because each entry should be 0. Now if you take x2 equals 0, and also we can take that x3, x4 and xn all are 0. But if we take x2 is equal 0, from the relation x1 is equal x2 plus 1, you will get the first entry is 0. So therefore this Rn, 0 of Rn, which is all entries are 0, is not in the set of W. It cannot be. So W does not contain 0 of Rn. So we can conclude that this is not a subspace of Rn. So in general, the vector Rn, a vector from in the W can be given as x2 plus 1, x2 and xn. So same way we can take it y2 plus 1 and then y2 yn, this is also belongs to W. So this is the second way to verify that W is not a subspace. So now if you add them, just x plus y, then you will get it here x2 plus y2 plus 1, then x2 plus y2, and so on xn plus yn. Now look on this, in the first entries is x2 plus y2 plus 1, and second entry is x2 plus y2. If you subtract them, then it is difference is 2, not 1. So therefore it's not belongs to W. So W is not a subspace of Rn. So we finish the third section of our course of module, and in module 1 today we are going to discuss the fourth one, and we left with another two. So let's come to the definitions of the basis. So for that we will discuss about the linearly independent and the span of the set. So let E be a subspace of Rn, and S is a set from the subspace E. And we say that S is linearly independent if we take the linear combination of the vectors, then all the scalars should be 0. If it is, then we say that the set S is a linearly independent. If it is not, then it is a linearly dependent, and it's not useful for our discussion in the basis and dimension. Next important thing is that is a span. What does it mean by the span? That S is a subset of E, the subspace E. Then if S is generated, we call S is generator or the span if every element of E is a linear combination of the element of S. That is, for any arbitrary E belongs to E, we can write that E as a lambda 1 U1, lambda 2 U2 plus lambda p UP for some lambda 1, lambda 2, lambda p, the scalar. So if we can write it, then S is a span of the subspace E. Then we have here the definition for basis. So if you have a linear subspace of Rn, then S and is a set as we take it before, then S is a basis of E if S is linearly independent and S is a generator of E. So we will take the very elementary definition examples for this. And before that, let's discuss about the dimension. So if the set has a p number of elements, then the dimension of the space E will be P. Okay, so it cannot be the more than n. So S should have the number less than equal n because it is a subspace of Rn. So therefore dimension will be either n or less than equal. So let's have a basic example here. We will have V is equal R set of real number, and then take the set S is equal 1. Then you will see that any V1 belongs to R. We can write as V1 is equal V1 multiplied 1. So therefore V1 is a linear combination of the entries of S. So this implies S is a basis of R and dimension of S is equal 1. So dimension of R is equal 1 because S has one element. So now we are going to generalize this concept and we will see what is the dimension of Rn. So in this theorem we are going to prove that dimension of Rn is equal n. So to show that we are going to take a set S is equal E1, E2, En. So where E1 is defined as 1, 0, 0. E2 is defined as 0, 1, 0, and En is defined as 0, 0, 1. So now to show S is a basis, we will show two things. One is S is linearly independent, and second is S is span or generator of Rn. So let's first show the linearly independent. So alpha 1 E1 plus alpha 2 E2 plus alpha n En. This is equal 0, 0, 0. Now if you combine them, so you will get it alpha 1, alpha 2, alpha n is equal 0, 0, 0. Now from there we'll get it comparing two entries of Rn. We'll get that each component should be equal. That is alpha 1 should be equal to 0 and alpha 2 is equal 0 and alpha n is equal 0. So this implies the set S is this implies the set S is linearly independent. So we are left with that the second property, which is S is a span of Rn. So to show that, let x1, x2, xn belongs to Rn. Then we can write this x1, x2, xn as x1 best 0, 0, 0 plus 0 x2 0, 0, 0 plus so on plus 0, 0 x n. So this can be written as x1 1, 0, 0 plus x2 0, 1, 0 and this continue plus xn 0 0 1, which is nothing but x1 e1 plus x2 e2 plus xn en. So therefore, since x1, x2 and xn is an arbitrary element of Rn, S is a span of S is a generator of R. So therefore, dimension of S is equal n. Okay, the set S which we defined in the previous theorem and in the proof of the previous theorem, and it is known as the standard basis. Now the question is here, does this is the only basis of Rn? We'll find out the answer after some slide. Okay, so now we have a subspace of R4 and the question is that find the dimension of E. So what is the dimension of this subspace E? So therefore, as it is a subspace of R4, the maximum dimension will be 4, but since it's subspace, it can be 2, it can be 3, it can be 1. So we'll see that how we can summarize it. So therefore, you will see that the entries for E on R4 have a restriction this 2. So therefore, we will try to find out what is the exact form of E. So now it is given that x1 minus x3 plus 2x4 is equal 0. Here we get it. X1 is equal x3 minus 2x4, and it is also given that x2 is equal 0. So therefore, the entries of E have the form x3 minus 2x4 and then x2 is 0, x3 as it is, x4 as it is. This is belongs to E. Now we will see that this can be written as x3 minus 2x4 0 x3 and x4. This is, we can write it as x3 and this is 1 0 1 0, and then we'll have x4 plus x4 and this is minus 2 0 0 1. Okay, so with respect to this, so therefore the set S is equal 1 0 1 0 minus 2 0 0 1 is a generator of E. So therefore, maximum possibility that this S is a basis and this dimension of E is equal to. But for two bases, so the basis we need to show this is a linearly independent. So let's have alpha 1 1 0 1 0 plus alpha 2 minus 2 0 0 1. So this is equal alpha 1 minus 2 alpha 2, then 0 alpha 1 and then alpha 2. So this is equal 0 0 0 0. So if you compare them, then we will get it here. Alpha 1 is equal alpha 2 is equal 0. So therefore S is linearly independent. So this implies S is basis of R, basis of E, and this will gives you dimension of E is equal to. Okay. Now we have a theorem, and this theorem says that if E be a linear subspace of Rn and S is a subset of E such that dimension of E is equal number of elements in S, then following three statements are equivalent. One is that S is a basis of E. Okay, so since it is a basis of E, it should be linearly independent and it should be generator of E. This three property will satisfy if dimension of E is equal number of the elements in S. So therefore, if you take any S and you already know the dimension of E, so let's dimension of E is equal some number, let's say 5. And if you say take any element of S, okay, containing the 5 elements, then automatically E is a basis of E. S or implies that it is linearly independent and it is a generator of E. Or in other words, you can say if you are able to prove S is linearly independent, then it will be automatically a generator. It will be automatically a basis of E. So therefore, in such cases, you don't have to prove that it is a generator or or togetherly you don't have to show that it is a generator or it is a linearly independent. If you can able to show just the linearly dependent, then or if you can show that it is a linearly independent, then automatically it will be a basis for the subspace E. Okay, so with this we'll get it here that a set of n plus 1 vectors. So if you take n plus 1 vector from Rn, then it will be linearly dependent because Rn has a dimension n. So it can contain only n entries. If it is, then it will be linearly independent. Otherwise, if it is n plus 1, then it is linearly dependent. So from this theorem, we can easily say that this V1, V2, V3, and V4, if we consist a set of these vectors, since there is a 4 vector, but it belongs from R3, so it is linearly dependent. And you can show that by using the definitions. That means if you take alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 plus alpha 4 V4 is equal 0 0 0, then you will get that some constant are not equal 0. So therefore this will be linearly dependent. Next example we have here that set V1, V2, V3, it's from R3 and only have 3 entries, but it is still linearly dependent because it's contain the 0 vector of the subspace. So, but we can prove this is also this way, V3. So this is equal 0, 0, 0. Now if you combine them, since alpha 1 V1 v1 have all 0, so it will be 0. So alpha 1, to express it I am writing another way. So alpha 2 v2, so this will be 0 alpha 3, and this is alpha 2, and this one is minus alpha 2 plus 3 alpha 3. This will be 0 0 0. Now we take alpha 1 is not equal 0. Still, this can be written as alpha 3 alpha 2 minus alpha 2 plus 3 alpha 3. This is equal 0 0 0. So this will gives you alpha 2 is equal alpha 3 is equal 0, but alpha 1 is not equal 0. So therefore the set v1, v2, v3 is linearly dependent. Okay, so from that previous theorem, we can, if we can apply on Rn, then it says that any set of n linearly independent vectors in
Thus,
Rn
we
is a
have
basis
completed
of
4 topics
Rn.
in module 1, and we remain with 2 topics, and we will come up another video and cover these 2 topics.